In 1941, the sci-fi legend Isaac Asimov wrote a story called Reason. He imagined a future where we built massive stations in space to harvest the sun and beam that energy down to planets. It sounded like magic, but today we are flipping Asimov's idea on its head. Instead of beaming the energy down to Earth, we are sending the computers up to the energy. Welcome to the AI with Arun show. We are about to dive into the most ambitious engineering project of the 21st century, space-based AI Superclusters. We're talking about massive data centers orbiting 650 kilometers above your head, running on infinite solar power, and cooling themselves in the freezing vacuum of space. By the end of this video, you're going to understand why the future of AI isn't in a server room on Earth. It is in the stars. So why leave Earth? It sounds expensive and dangerous. The answer is simple. We are hitting a wall. Right now, AI is growing faster than our power grids can handle. By 2026, data centers are projected to consume over 1,000 terawatt-hours of electricity a year. To put that in perspective, that is roughly the same amount of electricity consumed by the entire country of Japan. But it's not just power, it's water. To keep chips cool, terrestrial data centers drink billions of gallons of water, often competing with local communities during droughts. We call this the terrestrial infrastructure wall. We have a decoupling problem. AI wants to grow infinitely, but Earth has finite resources. If we want AI to keep getting smarter, we literally don't have enough plugs or water pipes on Earth to support it. The solution requires a grand reconfiguration of how we build the internet. Meet the Orbital AI Supercluster. The concept is brilliant in its simplicity. Instead of burning coal or gas on Earth to power a GPU, we launch the GPU into orbit. Up there, we have access to two things that are scarce on Earth. 1. Unlimited energy. Direct access to the sun, which is essentially a giant fusion reactor that never turns off. 2. The ultimate heat sink, the vacuum of space. This isn't just a satellite. It's an integrated platform combining gigawatt-scale solar harvesting with high-density Nvidia or Google chips. We are moving the compute to the energy, turning the vacuum of space from a harsh environment into our greatest economic asset. Let's look at the physics, because the numbers are staggering. On Earth, solar panels are okay, but they suffer from atmosphere, clouds, rain, and the fact that it's nighttime half the day. Their efficiency is usually around 25%. But in low Earth orbit, there are no clouds, no atmosphere, no night. The sun blasts the panels with 1,361 watts per square meter, a number physicists call the solar constant. This means a solar panel in orbit generates about 13 times more energy than the exact same panel on the ground. And it does it with 95% reliability. In space, solar isn't alternative energy. It is baseload power, reliable enough to run a supercomputer 24/7. Now, you can't just put these supercomputers anywhere. You have to put them in the Goldilocks zone. We use a specific path called a sun-synchronous orbit, specifically the Dawn-Dusk configuration at 650 kilometers altitude. Imagine surfing a wave that never breaks. These satellites surf the terminator line, the border between day and night. This means they are in a state of perpetual sunset. The solar panels face the sun forever, never entering Earth's shadow, while the radiators face the dark, cold side. It is a hack of orbital mechanics that gives us free, continuous power. Here is the hardest engineering challenge: cooling. On Earth, we use fans to blow air or water to carry heat away. But in space, there is no air. Space is a vacuum, which acts like a thermos. It traps heat. If you ran a gaming PC in space without a special system, it would melt in seconds. To fix this, we use radiative cooling. We have to turn that heat into infrared light and beam it out into the universe. We use the Stefan-Boltzmann law, which basically tells us how much heat we can dump based on surface area. Engineers have designed massive radiator fins that face deep space, which is minus 270 degrees Celsius. These fins can dissipate about 770 watts per square meter. It allows us to cool massive AI clusters without using a single drop of water. Okay, so we have power and cooling. But how do the chips talk to each other? You can't run a fiber optic cable between satellites moving at 17,000 miles per hour. The answer is lasers. We call them free space optical interconnects. These satellites fly in tight swarms, sometimes just 100 meters apart. They shoot lasers at each other to transfer data at speeds of 10 to 100 terabits per second. To keep them from crashing, they use AI flight controllers to solve the Hill-Clohessy-Wiltshire equations in real time. It's like a synchronized ballet in the sky, creating a wireless motherboard that spans thousands of kilometers. Hill-Clohessy-Wiltshire, HCW equations, are math formulas that predict how two nearby satellites move relative to each other in space. Imagine two cars circling a racetrack. The leader goes steady laps while the follower bobs slightly ahead/behind or side to side. HCW math tells you exactly how to steer the follower to catch up without crashing. Engineers use HCW for docking, like SpaceX Chaser to ISS, satellite swarms flying in formation, or avoiding collisions, all without full supercomputer simulations. Let us now meet the players. Google is working on Project Suncatcher. They plan to launch a cluster of 81 satellites. They've already tested their Trillium chips to survive radiation. They found that their chips can last years in orbit without failing. Then there is StarCloud, formerly Lumen Orbit, backed by Nvidia. In December 2025, they actually did it. They trained a small AI model called NanoGPT on a satellite using an Nvidia H100 chip. They've already secured a contract worth $13 billion to build a 5-gigawatt cluster. They are building the energy-as-a-service grid of the future. But the West isn't alone. This is a new space race. China is building the three-body computing constellation. They launched their first 12 satellites in May 2025. Their goal isn't just training AI, it's sky sensing. They want to process spy satellite data instantly in orbit, rather than waiting to send it down to Earth. And then there's Lone Star Data Holdings. They aren't stopping at orbit, they went to the moon. In 2025, they landed a data center on the lunar surface. Their pitch is resiliency. If a war or climate disaster wipes out Earth's internet, the backup drive is safely stored on the moon. You might be thinking, rockets are expensive. How is this profitable? Here is the magic number: $200 per kilogram. Thanks to reusable rockets like SpaceX's Starship, launch costs are crashing. At the same time, electricity prices on Earth are skyrocketing. We are reaching a crossover point. Once launch costs hit $200 per kilogram, it actually becomes cheaper to launch a data center into space than to pay for 10 years of electricity on Earth. The launch is expensive, CapEx, but the energy up there is free, OpEx. By the mid-2030s, space will be the cheapest place to train AI. Of course, it's not all smooth sailing. We have two big enemies. First, radiation. Cosmic rays can hit a microchip and flip a 1 to a 0. This is called a bit flip, or single event upset. While the processors are tough, the high bandwidth memory, HBM, is fragile and needs heavy shielding. Second, the launch paradox. Operating in space is green, but getting there is dirty. Launching thousands of rockets creates massive carbon emissions. To make this truly sustainable, the industry has to invent new green launchers that don't pollute the atmosphere. Then there are the lawyers. Space law is currently the Wild West. We have the ITU, International Telecommunication Union, trying to manage radio frequencies so satellites don't jam each other. They have a use it or lose it rule. If you don't launch your satellites within a few years, you lose your license. And what about data privacy? If your data is processed in space, which country's laws apply? Does GDPR work on the moon? Lawyers are now writing contracts that apply throughout the universe. Plus, there is the threat of war. If a country blows up a server in space, the debris could destroy everything else in orbit, the Kessler syndrome. Security is a massive concern. Kessler syndrome is a scary chain reaction in space, where junk from old satellites and rockets collides and breaks into more pieces, making even more crashes, until orbits become too dangerous to use. So where does this leave us? We are entering the era of the intelligence export economy. By 2035, nations won't just export oil or cars, they will export intelligence, beamed down from the sky. We are moving from an economy based on digging resources out of the ground, to one based on harvesting the infinite energy of the stars. The next Google, the next Amazon, the next AI breakthrough won't be built in a garage. It will be built in low Earth orbit. Thanks for watching. If you want to keep up with how humanity is upgrading its operating system, hit that like button and subscribe to the AI with Arun show.